हेलो एवरीवन। सीरीज में और इस सीरीज में हमारा एक ही ऑब्जेक्टिव है, मेक इंडिया सेमीकंडक्टर रेडी। राइट, वी वांट टू मेक इंडिया सेमीकंडक्टर रेडी। इट मींस इट शुड रीच whatever your age, whatever grade you are in, does not matter. What matters is that you find synergy and you see the excitement which we have in the semiconductor industry, right? Given the different kind of discipline, and what discipline is something we have divided, but different kind of knowledge background which is needed to make it work, right? And that's what we are looking at. So hopefully you would find some excitement towards something to explore more, and that is the idea. And that's where you would see how can I make myself semiconductor ready, so that if I want to work in this area, I can find an opportunity, good opportunity for me, or I could even open a company or an enterprise which could solve a problem. So basically, in the end, you have to understand the problem which are there in the industry if you want to open any enterprise, and see how can I fill that gap, right? That is the whole idea. And my goal for starting this series is to make India semiconductor ready with whatever experiences I have had in this industry, right? So today we are going to talk about yesterday, when we were looking at that lecture, we were looking at small video about the system. So we were thinking about why there is a need for a system, right? So now we would go a little more into that, where is the brain of the system is, right? So we have talked about brain of electronic system, right? And as we said, brain of electronic system is, you would, and we were talking about this board, which is a microprocessor, microcontroller, right? Which is basically on a motherboard, right? Some board, and this is what is the brain. Which, if you see most of the system, there is a board which is consisting of multiple devices there, which is making it possible. But now, where is the actual brain? If you were to see, it is inside this computing unit, right? And this computing unit is sometimes, if we used to, when we used to use desktop computers, we used to call it CPU, right? Central processing unit, right? Then when we saw that, okay, there was a lot of demand for games, there were different graphics and everything. So then this GPU became very famous at that time, or it started supporting CPUs, because CPUs were designed for general purpose task, right? So what we'll look at a small description of that, what are these tasks, but in some other video. For now, our goal for this video is to go about discussing what is this computing unit, right? So what is that? What is it made of? What is the typical architecture which it has? So if you see this CPU, and then there is a, this is designed for a general purpose task, means you can run, let's say, a calculator, you can run whatever apps or the different kind of computations you are running, it would do its job, right? Do it efficiently or not, that is a different question, but it is going to do that job. Now graphics is something where they are designed for a GPUs, which is called graphical, right, processing unit. And if you know the AI era, you have probably heard of GPUs from NVIDIA. They are designed for a specific task, right? So now you started seeing that we are going from a general purpose task to a specific task, and the computing unit name and even the design, everything will change. Similarly, if you go to more specific tasks, which you probably hear from Google, it's called TPU. This is again for a specific task. So for example, this is called tensor processing unit. And who knows, next one, maybe you are going to invent? Which is the next? What is the next? But before that, you have to actually understand what is this specific task it is doing, what is the demand of that task, and if you were to design that architecture or that kind of processing unit, how it has to be designed, right? So that specific task, let's say for GPUs, it could be, for example, matrix multiplications, right? So that means if you are multiplying very big matrices, probably GPUs is doing much better job than CPU. Much better means in lesser time and in lesser energy. So that is what would mean. So how do we distinguish them? If you see, there's something called, which we say latency and the energy consumption. So these are the holy grail, how you will say that they are better or worse. Latency means that how much time it would take when you apply an input for the output to come out, right? So that is the latency which it had got through uh, from applying the input to getting the output, right? But now the energy consumption is another metric, which is like how much time, how much energy it is consuming in doing that task, right? So that is the, and then you will see that these are the simple ways you could compare these, and they are designed for very specific tasks. Now, if you were to, so briefly, we will just look at inside CPU, what is there, right? What is the typical architecture inside a CPU? So if we see this computing unit, obviously this is made of semiconductor, right? I mean, there's semiconductor inside this. Otherwise, we would not be talking about it, right? So we know or not, the semiconductor is inside a CPU, inside a GPU, inside a TPU, right? Because it's made of semiconductor devices or semiconductor components. So now, if we look at what this computing unit is having an information, so you could, so that is the way typically you, if you want to understand this field, my recommendation will be always to draw a block diagram. Understand what is the input output of that block diagram, right? So for example, in computing unit, we are giving some input, which is a data. The information is coming again in output, right? And while I draw this thing, it means that there could be only one line or there could be multiple lines which are coming, right? So input is not just that one, it is coming only at one terminal. There could be multiple nodes the input is accepted, right? And that is the reason why you see in the terms of your computers, you, if you hear this 32-bit CPU or 64-bit, the meaning is just that it is able to accept 64 bits of data, right? And this bit and everything, the small terms we will define in another video again, right? So that we can understand them. And these are, they will be linked also to this video, because if you want to go to that video to understand those terms in detail, right, you can. That is the whole idea of the series, that everything is connected, right? And we want to understand what is happening. So if you see this 32-bit of 64-bit, and that is the input output which you are having typically, right? The information is going in, information is coming out. Very simple example of that is, let's say I'm summing A plus B. So 1 plus 1, right? One goes in, one goes in. From here, 2 comes out, right? If I'm doing a sum. So that is the way you would see this, and this is obviously very trivializing the use of computing unit, but that is the one operation we can see. So now, what makes computing unit do this, right? So, and that, let's start with just our example. So we said we are putting in this computing unit, we are putting, let's say, one here, and 2 is coming out, right? So this is our processing unit. Let's call it PU, right? Processing or computing unit. So then if 2 is coming out, then what is happening? So obviously, when it is going in, there is different ways I could do this operation. And in the, when the CPUs are designed, right, as of now, right, and everything, we convert first this information into whatever we are getting into a digital information, right? And that means that information which is coming at input is converted to digital form. So digital form means, I think you know, the digital form means that it is going to be in the ones and zeros, right? So stream of ones and zeros. So that is the meaning of that converting in digital form. Now that digital form you are giving to your processing unit, right? And you are computing that, or you want that output to. So obviously it's going to compute in the digital domain even. So this is, so very simply I could understand this, that there are this one and one which is coming is given by some block, which is, let's say, your ADC, which is called analog to digital converter, which we will talk somewhere. For now, the meaning of that is that this 1 volt which I am giving is an analog domain, right? Because it's a 1 volt which you are giving. So that means similar to, let's say, when you have battery, the battery, whatever you are getting from the battery, if you see directly, it's a, let's say, 5 volt or 3.3 volt, whatever, right? So that input, if you give, it may convert based on whatever coding you have done inside this block called analog to digital converter. You will do some coding. So then it would convert that data into the stream of bits, let's say 1001, whatever it is, right? So similarly, it is going to convert to like this, right? This information. So now when it converts to this information, which is digital, the processing unit also gives a digital output, let's say, right? Something like, say, like this. And then this has to go through again a block, which is your digital to analog converter, and then you will get to. So that is the meaning, that how this is going to process this information, right? Now, quickly, what is going to happen inside the processing unit is what we are interested in, right? Just to understand at the block level again, that what is happening inside. So when I give this data into digital bits, right? And these digital bits are going to be added to, that means they are going to be added sequentially or parallelly, whatever it is. But I would need some kind of memory. So let's say this is my processing unit. I would need some kind of memory so that I can store this data, so that it is not lost, because I have to give this stream, whatever is coming out 100, right? So there is a memory which is going to be there. That means it's like how our brain is computing. There is a memory. So when I store also, like somebody is, it's like a thing that somebody is giving you a lecture. You are thinking of a question, right? You don't speak at that time, right? When the somebody is speaking, you speak afterwards. So where is the data stored till the time you speak? It is obviously stored in the memory. Similar to that, your processing unit also needs to have this memory, right? But the data, when it is processed inside, it is happening inside something called where the computing is happening, right? And computing means where you are doing actually a sum of this. A very simple example of computing could be a gate, right? And I think you have heard of gates. If not, there would be another series on gate. But as of now, gate is something like which you give information at the input. Let's say you give 1, it converts that information into some other form. So let's say a 0, because it's a NOT gate. NOT means it converts or inverts the information. There could be another example is, let's say, your AND gate. You're giving 1, 1, then it converts to 1. But if you give 1, 0, what does it convert to? Because it is going to do AND operation. AND means if both of them are 1, then only it would be 1. Right? It's a very similar to any logical thing we have seen, that if both conditions are true, right? Then, so this is similar to if we write, if in 1 is equal to 1, and if we write into equal to 1, right? This is this construct in the algorithm we will see. So this AND means that this is going to AND do that. If we do or that would be another gate which you will see for or, right? Where you are applying 1, 0, it would give you a 1 output. Here it was giving a 0 output, right? So these are the simple gates which are powering or which are inside this computing unit and making it possible. And that is why we see that these computing unit, they would not obviously remain in isolation. They have to talk to each other quite frequently, right? Both ways. So that means data going from memory to computing, compute comes back in the memory, then given out to the output device or whatever our deck was, right? If we want in a digit analog format. Similarly, the data which is going to the computing units or the memory in the digital format, right? So that is the importance. If you see, that is how typically a CPU is designed, right? What is inside this, how does it look like, we are going to see in another video. But this, I think, gives you an idea what these processing unit, where the brain of this is happening.